Next question is, how do we measure values that we can barely imagine? Take, for example, IBM's latest supercomputer, which is said to do calculations at the rate of 1 petaflop. A petaflop is 1,000 trillion operations a second. That's, I'll just count them out. 1 with 15 zeros after it. So my question is, it's impossible to imagine how can you even measure it. Which brings me to Jun Ye of the Joint Institute for Laboratory Astrophysics in Boulder, Colorado. Now, he's created a clock so accurate that it'll neither gain nor lose even a second in 200 million years. This outperforms, right? Because boys are competitive. The official atomic clock used by the U.S. Commerce Department's National Institute of Standards and Technology, which is only good to 1 second in 80 million years. What a bunch of duffers, eh? So apparently the secret is speeding up how fast the clock ticks. And Jun's new timepiece, I'm reliably told, ticks 430 trillion times a second. It's hard to conceive. You might ask yourself, well, why do we want to do that? Well, it turns out that highly precise clocks are critical for deep space navigation and exploration, where even the slightest error, and we mean the slightest error, can make or break a mission. Jun Lee, come up here and tell me how you deal with all of that.
Well, it's a great honor to be here, and thanks for the kind invitation and the kind introduction as well. And hopefully by the end of the day today, my task is to entertain you and share a little bit of passion for precision measurement, and in particular making an atomic clock. And I hope by the end of the day, even if I cannot convert you into a clockmaker, at least you will be able to know, appreciate the very basic science and technology goes into making these kind of devices. So a laser that's brought in from Boulder, this green light that you're seeing here, can actually tell your time in the future. And how can we do that? Can you actually see, as you look at this laser pointer, do you see the wave going by? It's too fast for the eyes to see, but how do we actually can count that? That's really the story for the next 20 minutes. This is going to be the clock I'm going to tell you. It's going to be some atoms, and we're going to shine laser light, capture them in somewhere, and then use a rainbow of light to distribute the time from this really fast light that you cannot visualize with your bare eye or any electronic equipment, but turning them into a clock that can give you the most accurate measure of time. And of course, clocks are really everywhere. I think Moses has already mentioned some of the applications of the clock. But in fact, for example, going from drill for oil, I know this is on the mind of many people these days, to semiconductor wafer, making very accurate computer chips. All of these trace their standards. You need rulers. You need something to measure what you're making. All of those can be traced back to the time standard. Another, perhaps most pervasive use of clock is in deep space navigation. Suppose you're going to land an unmanned vehicle on the surface of Mars, or you're going to communicate on the global positioning system, where all these satellites are in synchronization with airplanes, with on-ground communication centers, and so on. So it's a great use of clock for space explorations, for defense and homeland security. Why does it make atomic clocks so special? It all comes down to that we can actually use atom, and inside the atom, electrons moving around the nucleus, And what we are measuring is how fast these electrons are moving around the nucleus. And they move very fast. And so it comes down to it. It's always the speed that matters, chasing the speed. The reason is actually perhaps it's completely trivial. I think everyone sitting in the audience can appreciate this fact, is that suppose here's the 2 blocks, and I want to measure the distance between these 2 blocks. Here's a ruler. What you do is you put a wave in between. Or as a ruler, you will see the finer marking on the ruler makes more accurate measurements, right? You all have made measurements using rulers. So instead of having 5 waves, what if I have 25 waves? I know that using this blue wave, I'm going to be able to make more accurate measurement for the distance between the 2 blocks. So, but there's a problem. This sounds all fancy. You're going to count all these cycles, and if that works, then you are home free. You can really make very accurate clocks. But there's one problem. How do you count all these human hairs? How do you count them? And if it is in 1 second, 10 to the 15 human hairs flashing by your eye, you will have no chance ever to capture maybe 10 of them. The only way to count light ripples is light itself. You have to make a tool out of light to count those light ripples. Because that something runs equally as fast and very stable. So in the lab, we create a laser. It's no longer like the laser I have in my hand, which has only single color, green. In fact, this laser emits a whole rainbow, except it's much, much more intense than ordinary rainbow. And this rainbow of color is everywhere, covering the entire visible range. And if you zoom in, if you had a microscope, zoom into one particular area of this rainbow, you actually see there's a lot of tick marks. There's a frequency markers. It's as if you have made a ruler out of light. And that is a ruler we're going to use to measure an optical frequency. So if you have an optical frequency sitting somewhere, like the laser that's being held in my hand, a single frequency, single color, and we want to count how many cycles are in this color, we are going to use this ruler to count it. And this is actually a device, a cavity we created to be extremely stable, such that we can make this ruler very stable. And then, again, using analogy, this is almost like you build a gearbox where you turn the wheel on the visible light, and going through a reduction gearbox where on this end spits out radio frequency, that is the signal that you can use for your clock. To put things in perspective, excuse me, if this wheel is as large as a bicycle wheel, you all have worked with bicycles with reduction gears and so on, with 10-speed reduction gears. If this wheel is as big as a bicycle, then this wheel would be as big as the entire Earth. It's just because light frequency is so much higher than microwave frequency. And that's the reduction gear that we have essentially constructed in the laboratory, that we can now count the light frequencies. And so with the light in place, the only missing piece is now let's pick an atom that you can actually use that to make a very accurate atomic clock. And here's a periodic table. And we picked the atom element, which is called a strontium, not just because it sounds like a strong team, but it's a strong. And the reason is because it's actually a very simple scientific reason why we pick strontium. It's got a very special property. So suppose this is the landscape, and you want to have landmarks, and whether you want to pick a mountain with a very gentle slope or a mountain with extremely sharp slope, which one's better served as a landmark? Of course, it's this mountain which is very, very sharp, because once it's defined where it is, that position doesn't have as much error as the one with a very gentle slope. And the strontium serves that purpose. Now, imagine this is not a landscape in the real world, but imaginary world of frequency landscape. The strontium actually can provide extremely sharp landmarks where you can have your very stable laser to hook up to this mountain, and that mountain serves as a clock signal, and that's the atomic clock signal. But the first thing we want to do is to make sure the atoms are not moving anywhere. We are going to make very sensitive measurements now using these atoms. But of course, in reality, these atoms are moving everywhere. So the question is, how do you make sure these atoms don't move around? And we have a trick to do that. We shoot photons against these atoms. So when the atom is moving towards me, I shoot machine guns, like using photons, to make them stop. But of course, atom can move towards me, they can also move away from me. And then I turn on another machine gun from the opposite end to shoot against the atom, until the atom just has nowhere to go but it stays stationary completely in the laboratory. As you see here, before I turn on the animation, these are 6 beams of lasers that's shooting from all 6 directions to making sure the atom has nowhere to go but stay in the center. And not only they stay in the center, they actually get cold. So you will see this cloud of atoms get shrink down, and it gets trapped into the light trap of these red light. So as you turn on, you can see the laser fire, make these atoms extremely cold, they shrink down. And we actually do this twice using blue and red light, it gets further cold. And now you see these atoms pointing to one particular direction with these spins. Now the clock laser comes in, flip those spins, and those are the information of the atomic information of the clock. And then we can read them out by, again, turning on these lasers, and these atoms will give you the information of where you are with respect to the atomic resonance. And these information will be used to this frequency comb where we have a rainbow of colors, and that turns into this clock that can actually be related to the watch that you have. So that's the basic principle of atomic clock. With that, we were able to recover a spectral line shape. It looks like a mountain now in the frequency domain. In this imaginary landscape of frequency, you get this very sharp peaked line, and we can stable our laser to exact top peak of this atomic resonance, and that's your clock. And in fact, this is a visualization of the light ripple. Remember, those lights were oscillating 10, 15 times per second. And we said there's no way we can visualize these light ripples. But here is actually a real picture of the light oscillating back and forth. That's because it's being regulated by something which is equally as fast. And creating, remember this rotating wheel picture, creating a signal that you can use as a clock. And we were able to achieve accuracy, which is, if you count how many zeros, instead of, in fact, we made it 10 times better, not 15 zeros. There's actually, here are 15 zeros, but it's actually 16 zeros plus minus 1. And then, of course, the work wouldn't be possible without a really fantastic team of graduate students and postdocs that my co-workers in the laboratory. And some of them have gone on to be professors of themselves. And also, I think the dream is alive. This is a futuristic picture where you're putting interferometers in the space, 5 million kilometers distance between satellites. Here's Earth and the Moon. This is the Sun. The task is to keep the distance between these satellites to be a 1/1,000,000th of a fraction of a human hair. And so you use laser light to keep a distance. At the same time, that laser light tells you the time. So that's everything, all in one. Space clock and laser ranging in one. You can measure distance, you can measure time at the same time. So thanks very much. Thanks.
There. Now, that wasn't that complicated, was it? Jun, I want to ask you, is this something I can wear on my wrist? I mean, like, is this a huge building? Is it a little device? Like, could we package it up in this nice little cuckoo thing?
At the moment, the system is way too big. It, in fact, consists of 4 tables of equipment. And so it's not ready to be very compact. But the U.S. military is definitely very interested in making this to be very small.
Really? Well, put me down for, like,
yeah.
I'll buy one of the first ones. Okay?
Good. That's a deal. Thanks.
Thank you very much.